First, welcome and thank you for coming. I know this issue might be a little bit controversial. Not issue, but the subject of the talk, and maybe heretical. So the presentation will be about what we did at CERN to connect different systems. And I would like to start with this slide to show you, maybe to help you decide whether you want to continue in this subject. Our challenge was to connect two different systems. One is written in Python, the other one in Java. And we found a solution, and our solution allowed to connect those two systems. If you imagine these thousands of Django websites, so we may manage to connect those two systems together in a very tightly coupled way. You can run any Python application inside Solr, and what is more, you can control Solr from inside Python. That's one thing, and including in this extension, you can run any C or C++ application that Python can connect to. You can run it inside Solr. So think about all these libraries for scientific computing, statistical analysis or machine learning that are written in C or C++. So now it's very easy to include them inside Solr. Maybe some of you prefer to check out the source code while I talk. You can read it, and for the rest of us, I will say a little bit of details following this slide. So CERN is located in Geneva, in Switzerland. It's a very large research institute. Here you can see it from above. The red ring is the tunnel, 27 kilometers long, running underground. Inside, there are magnets and people built very huge, scientists built very huge detectors and cameras to study particles. It's the place where we kind of find it funny to study and to play with things, in this case, cryogenic magnets. And it's the place where it's actually supported to create collisions for about 40 million times per second. And this is the result of the research. So the community is 40 to 50,000 scientists worldwide. And when they need information, they, in the past, created something called SPIRES, bibliographic database. It contains only metadata, no full text. But what is interesting, this was the web that started, it was the first searchable database online in the States, created just 20 miles from here in Stanford. And it's also interesting, the SPIRES system itself is the oldest software I know, created 1967, and pieces of it actually still runs in a inside emulator. And you can, well, this was the first interface. This is how it looks like now. You can search, it's a bibliographic database, contains the keywords, authors, titles, publications, and so on. And we decided to create a new digital library called Inspire. And this one contains also the full text and services built on top of it. So in one of those slides, you can see the plots extracted from the articles, from the papers, scientific papers, including citation analysis, different searches, full text searches, access to papers, and so on and so forth. Now we are getting to our challenge. The digital library is built on a platform called Invenio, and this platform is very flexible digital library software built at CERN since 2001, and it's also very big, almost 300,000 lines of code, and you can find it. Installations of Invenio are usually in a quite complex and are among the top 5, the biggest repositories, institutional repositories worldwide. So the software itself is very flexible. One of the very cool features is the citation analysis. We can look at the maps of authorships between amongst the papers, very many levels far. And this system is written in Python. So obviously that shows you what was our problem. Our community of scientists still likes to search in the metadata, and a lot of ranking is sorted by the latest search, because they follow the field and they are interested in the latest papers. But as we ingest more and more full text, we need to come with the better search. So just to illustrate the example, our initial thinking was we have 2 different systems. One of them is Invenio, that's the one, and the external search engine. And let's imagine we have a query, and we would like to outsource part of the query to the external system, just part of it. So we send, for example, the full text search to the external system. The external system returns IDs. We have to translate the IDs into our internal IDs. Then we do the second part of the search, create the intersection of the sets, do the ranking, filtering, sorting, and display the results. Okay, so far, so good. That's not difficult. But the challenge in our case, we have to shift between 1 to 6, sometimes 10 million of IDs for the search because of the citation analysis. So we have to shift that volume of data over the line or somehow. The first thing to note, if we shift only the IDs, we miss the scores. So we cannot rank the IDs. We can do it very fast, but we cannot sort sometimes. If we provided we have the scores, still we have 2 different systems, and it might be difficult to merge the scores because they are computed based on a different metrics, based on the different indexes. And the other problem, sometimes we would like to push several millions of IDs to external system and ask for faceting. So you might say this is not exactly the straightforward communication or the protocol data structure. So, well, I have to say we love Python, and you probably love Java. So I understand that I'm in the field where Python might be thrown upon. We decided we cannot. It's not good to extend our own application. It's still our main application, but we have to make this shift and look at it from the other side. So maybe because of the search libraries are written in Java, what about if we extend the Java library using our own service? So still we want to shift a lot of IDs very fast between these 2 systems. For our case, the latency of 1 to 2 seconds is okay. We want to leverage the power of both systems. Like, we don't want to lose our citation analysis, and also we don't want to lose the cool features of the Solr, for example. We would like to also make it simple. So let's review some of the options that are available to us if we want to connect Java applications. Well, let's say you have Java application. I have to admit that I started hacking Solr before I knew how to index documents, and that happened a few months ago. So I still may have some gaps. So I would be happy if you correct me, or if you provide more information. But from reading the code, I think I found the standard ways how to connect the applications. Just to review them, if you have Java or C and you would like to include Solr inside, the standard way is to use the class called embedded Solr server. And basically, we just create instance of the Solr with the configuration. And when we want to communicate with this instance, we have to create the Solr request object and Solr response object and fill the request object with the data. So we kind of, we do the same thing as the servlet containers. And sometimes it might be additional work. But this is the standard way. The only catch is when Solr is returning results, it's always using the XML writer. So all the results will be parsed by XML. That might be not operation which is not necessary. The other way to connect applications or embed Solr is to use direct connect class, which I found very nice or flexible. It's similar to the embedded Solr server. We create again instance of the server, and now it's called direct Solr connection. And we don't have to create a Solr request object, and we don't have to create Solr response objects. Everything that we pass in is a string. Everything that we receive is a string. This is nice, but obviously this might be also a little bit slower than the previous. And if we are too lazy, maybe we can just embed the Solr servlet, the Java servlet. This worked quite fine. If we get handle of the Solr instance, we can call the Solr instance and pass the objects, and also we can take advantage of the HTTP communication. But in our case, we are not Java application, and we want to get connection between Python and Java. I will skip things like we could write our own Java native interface connecting Java and C, but this really would not be anything simpler or fast or error prone in our case. So these were the options that are possible. And I have to say that remote object calls would be too slow in our case, especially with Python, due to the protocol serialization and deserialization. So really the remote object calls are not something that we wanted to go to. We implemented actually pipes, and we are able to shift 10 millions of IDs in about 50 milliseconds. And when we want to move these records from the Java to Solr, it can take 200 milliseconds, providing there is a Java object and on the other side there is a Python object. So creating these objects can take 200 milliseconds. But still, it's just a simple shifting of record IDs. The other options, more advanced, how to connect these applications is Jython. I think that everybody would say Jython is the right option to do it, but it's not, and there are two main reasons. It cannot work. First of all, in Python we use a lot of C modules to do things fast. For example, we have a special module for int-bit set communication, and things written in C cannot be used in Jython. They are working on something called the Java C extension API. So if you are interested, you will find a link to Notion of it, but it's still not there. And the other reason is that Jython is also quoted to be 20% slower than Python. So the two main reasons why we cannot go that way. But it would be very good option, very natural option in Python for us. You simply write code like this. Here you have a search engine in 14 lines. At the beginning, we import classes from Java packages. Everything is written in Python using Python syntax. But actually, behind the scene, it's Java that compiles this Python code and executes this Python code. That would be a very natural option. But unfortunately, it doesn't work due to these two reasons. Other two options are to use some sort of library that connects Java and Python application using a Java native interface. So Python code runs inside a Python interpreter, and the Java is doing its own thing, and there is this crossing between Java and Python. And I was looking at the project called JEPP. Here you have an example of a JEPP simple code. It's again the same code as previously. What is not so nice is this doesn't feel like a Python. We create a string, and then we pass this string to the JEPP. A JEPP will evaluate the string inside the interpreter, and then we can ask for to get the variable back. But this doesn't really feel like a Python itself. I didn't like JEPP myself, but there is another option when we want to include, connect these two things. And it's, maybe you are familiar with something called PyLucene. PyLucene is a port of Lucene. It's a very smart project, and it's the creator of PyLucene and Divida is Apache committer. And PyLucene is possible because there is a very smart generator called JCC. This JCC will take your Java application. Oh, it's using standard things from the Java, like Java H. Basically, it will take your application, look at the public classes, look at the public methods, will inspect the methods, and prepare a C++ headers of these methods. Simply put, we can take JCC and create a Python extension out of Lucene. This is the way how PyLucene is created with every release. I noticed that it was said during the previous presentations it will be very difficult to create the ports, especially for Lucene 4.0. But I think this doesn't really apply here because PyLucene will be able to keep steady pace with the development. Usually the releases of PyLucene are very fast after the release of Lucene. So this is a very nice way to connect Python and Java, but usually it's like we have a Python application and we are running Java inside. We create Java interpreter inside our Python. Here you have an example. The difference from the previous example of the Jython is only in the import. Previously, we were importing from Java packages, but inside when we use PyLucene or JCC, we import from one master package and those classes. Another difference is the fifth line, where we create a Java virtual machine. So Java is actually runs inside Python. Everything else remains the same, feels like Python. But we are working actually with Java objects, like they were Python objects. So to summarize it a little bit, we could not use Jython. The JEPP doesn't really look appealing, and JCC was the only option that was left to us. In the end, it looked like this. Our application called Invenio because I was lazy, so I took the whole Jetty servlet container, I've wrapped it with JCC and inserted inside. So in the end, we were running Solr web server inside our web server. But this is not a good option. Imagine for a moment that this diagram is a Java application. The blue thing is a Java virtual machine. The green outer box is a servlet Jetty container, for example, and the inner box is Solr application. This is let's take the simple example of the Java, where there is only one instance of Solr inside the servlet, and you would expect that in Java you can create very many threads, and when many requests comes, the threads will be working in parallel way. This is not possible in Python because of the nasty thing which is in the title called global interpreter lock. In Python, when we create several threads, they cannot really run concurrently. There's always one thread that keeps the CPU, the other threads have to wait. The standard solution for Python is to create several interpreters inside, in this case, inside Apache. In that way, we can respond to many requests. But still, we can have 200 threads, but in this case, only 4 threads will be running parallel. But what happens when we include Java virtual machine inside is this. We are using 4 times more memory, and there is a problem of synchronization. Like, only one Solr instance can open the index and write to the index. The other 3 instances will have to be read-only. So this doesn't really look nice. I described our problems, and fortunately, this is not very well-known fact. JCC can be used in both directions. If you want to include Java inside your Python, or Python inside your Java. I will describe how it's done, but it has very practical consequences. We can prepare our code in Python, and we can run it inside Java. The final setup looked like these 2 circles. We have our application, which is Python, the left one, and on the right side is Solr, standard Solr search service. And if we wanted to implement this bridge, what is needed, I will skip to the example here. If we want to write things in Python and have them accessible to Java, we first have to create this kind of Java class, which provides several native methods. In this case, it's the bottom line receive message is a native method, and the actual implementation of this method will be in Python. It really feels like as if you were writing your code in C, but the difference is that this is much simpler. You can provide the actual code in the Python. The JCC will take care of the intermediate steps. And all the rest in the Java class, it's the necessary code needed for gatekeeping of the objects. JCC will take care of keeping track of the objects that we create, the referencing them, releasing memory, and so on. So this is a great way to connect Java and Python applications, but it has a lot of complexity, other things that we have to take care of, and so we packaged this solution into one extension. The final setup looks like this. And I would like to give you an example how it works. Again, you can imagine this is on the left side is front end to it's our search application, our Invenio digital library. And when the request comes, we are asking Solr for the data. but Solr in this case is enhanced. It can do citation analysis and other things as our system. It works a very standard way. When you start your Solr, you just need Java virtual machine, the Solr jars, and the very first thing that we have to do in the main thread, we simply have to load the JCC dynamic library. On the Python side, we obviously need a Python interpreter and 4 modules that actually provide access to Solr, Lucene, and MontySolr is our extension, our code. These Solr, Lucene, and MontySolr modules are Java applications, and we compiled them into the Python application, Python modules using the JCC. So imagine this is your standard Solr instance. We loaded the JCC. And, well, the query arrives, and the Solr should answer this query. The custom handler is just the usual handler that we are writing when we extend the request base class. I will show you an example of the body of the custom handler. So we get the request object. This is still in Java. We got the request object from servlet container. The first thing we have to do is we create a Java envelope. We create a message, and we say this message should be handled by the perform search method. We fill the message with the necessary objects. We can put any Java objects there, request object, response object, and so on. And then we send the message on the second line. What happens when we send the object is that the Java envelope is traveling over the GNI interface. We have to make sure that this bridge is very short, because all the envelopes are traveling over this bridge, and they can go only one by one. The Python bridge is instantiated. It's a Python class that provides the native methods, but it's instantiated every time that we are calling it. So we are making sure this is very short and very, very fast. Then our bridge simply takes the envelopes. Oh yeah, I didn't say that what happened is that JCC, you can think of it like take the Java object, wraps it in the C++ interface, and passes it by reference to the Python object, to the Python interpreter. Python takes it and works with it as if it was a Python code. Here you have actually a real example. It's this part. We receive the message, and we get outside of the message the query itself. We call our system using the API. So this case, in this function, is the only one that we have to implement. And then what happens? We send the request to our own system and harvest back results. Another development that was possible, that wasn't possible with the Python at least 2.4, is multi-processing. The 4 Invenio instances that you see on the right side are actually 4 instances, 4 independent Invenio installations that are run inside our main interpreter. In that way, we can still have at least 4 threads inside Python, but they don't consume 4 times more memory because they are created, at least on Linux, they are created as they are forks. They share the memory. So this is a very nice way to to have several instances of Invenio respond to our request. So still, even if we are inside Python, we can be very fast, provided we have enough CPU cores. What happens? We simply got the objects from inside Python. Yeah, I would like to show you this. The last line in our function when we receive the hits from our system. This is the tricky part for Python programmers, because the message object is Java, well, it's a Java object with objective interface. What we insert inside, we cannot put there Python objects. We have to convert Python objects into Java. That's the not so pleasant one for Python programmers. But in the same way, we are able to control Solr from inside Java. So if you check out the code, you can find an example where we simply call I think it's Twitter indexing. We simply request, Solr gets a request from outside and passes the request to the Python. And inside Python, we take query parameters. We ask Twitter for documents, fetch the documents, and inside Python we create Solr document objects and also index them and update the index. Everything that what you can do in Java, you can also do inside Python. So the actual setup is a little bit more complex than what I've shown. Usually we have several instances of Invenio that are asking for data, and that's a search service on the right side that runs one Python interpreter with several instances of Invenio. Right, we were not sure whether this setup is really robust, it can work for us. So we did really extensive testing. I have just a few slides, but we did a lot of siege tests and other measurements. So just one slide with the familiar. You can see the on the left, in the left corner. When we look at the long-term running process of this setup, we saw that the memory was periodically reclaimed and detected no memory leaks. And this is quite crucial because we are creating C objects, and obviously the JCC takes good care of releasing or destroying these objects. We also looked at the performance, and here you have a comparison of when we exchange the record IDs between two systems. The tick line is Solr, Python included inside Solr, and this dotted line, the other way around. The tick line is communication over HTTP, exchanging compressed IDs, and the dotted line is the MontySolr, our Invenio inside Solr. So it's the function. Here you have see the seconds, and here are concurrent users. We were looking at the high load under the siege. So it was for 1 until to 100 users, concurrent users. What is the most important thing is that the direction of these lines. We didn't see that we can say it's slower, the MontySolr is slower than the exchange of IDs over the HTTP, but actually for being a little bit slower, we can do much more. We can control the Solr, we can access all the methods and all the objects inside Solr. The important part was that these two lines did not diverge very much. So we can say it's fine. And that was without caching, and because we are inside Solr, we can take advantage of all the infrastructure that Solr provides. So when we switch on the caching, we simply provide a service to Solr, And the response time went down to 1 second, and the median time was 6 milliseconds. For the full text, well, this was the test running 70,000 different queries over the index of 800,000 documents. So the tests show that we can really rely on this thing, at least for our purposes. Under the high load, the complex searches were fine. For what you see is 50 concurrent users. In the case of citation analysis, we are very often working with at least the 50% of the database. So that's why the load is much higher. And with the 50 users, but it's the function of we are more limited by the database than by the search. We did some tests, but they cannot be really reported as a real benchmarks. Comparing or trying to find out what's the difference between Python and Java. So some tests were like indexing and creating string objects and creating copy of the string objects, always forcing the code to create a copy of it. And when we compare Python and Java implementation using this setup, we can see that Python was 9% slower than Java. So no memory leaks it's a very good message, but if we are not careful, and we do something what we should not do in C, like trying to access the method of the C object which doesn't exist, this will bring down the whole server. Not only the Python, but it will kill also the Solr instance. But that's a Java native thing. It's true there is complexity added for the setup. We have to compile the extensions, but actually we have to compile them only once, and then we can provide the Python code that is using this simple framework, creating Python messages. Inside the message you can put any Java object, and on the Python side you receive the Python message and you work with it. So in this case it's very flexible, and you compile once, and you don't need to compile for the next methods. So for this, we get very tightly coupled integration between Python and Solr. Really the best of the two worlds. Now our Solr instance can do citation analysis. I don't know if there is Solr application that can do citation analysis or citation search. A lot of features for free because we take advantage of the infrastructure of Solr. When we retrieve results, I think, for example, today somebody mentioned the Jira issue 1715 of getting data from external sources, and that's what we do kind of naturally, what we had to do in our system. Simply, when we have a query, we can dispatch one part of the query to our system, this Python, that our system can ask the database or get the data from wherever they live, retrieve the data, and then pass these record IDs to Solr. And Solr will simply take those IDs and will work with them as if they were Solr Lucene record, or Lucene documents. And as I said, we can control almost everything of Solr from inside Python. So to wrap up, our challenge was to connect these two different systems, very different systems, and we wanted to make it simpler. It was not, we had to resist our love to Python, and we could not really extend our own application. But we kind of, I should not say sacrificed our application, but we inserted our application inside Python to provide services. And this extension is open source. You can check it out. And as I said, you can connect any, for example, Django websites with Solr, but the real cool thing that you can include these C and C++ libraries for scientific computing or machine learning, get that really in a very cheap way the resources that are available out there. So the address of the source code and our extension is quite new. We'll be very happy if somebody tries and gives it a try. Just let's you can work with us and we can make it better. We will see what we can do if you have some needs for your application. And if there are any questions, I can try to answer them if I'm able to. So the question is, in our case, how to deal with the Lucene document IDs, which are changing all the time. When, for example, when the document gets updated, or indexed, deleted, and so Lucene ID changes. In our case, we are simply using field cache. So when the document gets updated, the field cache is updated, and then we retrieve record IDs from our application using, for example, MySQL. We retrieve the doc ID, and the field cache maps doc ID to Lucene ID. So in that way, we always have the correct mapping. Thank you, and have a nice day.